Welcome student in our virtual classroom. It is the 26th lecture of Engineering Mechanics, and you can remember that in last class I have discussed the slider crank mechanism and the velocity study of slider crank mechanism. Today in this class I will going to discuss the same slider crank mechanism, acceleration formula, and how to solve the numericals on acceleration. And the slider crank mechanism that is observed in any engine. So it is the mechanism of engine where the rotating motion has been converted to reciprocating motion. Let's follow the lecture.
Let us consider a plane of rigid body, and it is rotating with a reference point O. Now within the body there is another moving reference system, small xy. About point B it is rotating in clockwise anti-clockwise direction. So here is the direction. Now omega and alpha, it is the arrowhead indicates the direction of rotation, but the vector omega and alpha direction is perpendicular to this plane of rotation. Now RB is the radius vector of point B, RA is the absolute radius vector of point A, and RAB is the radius vector of A with respect to B. Means it is the radius vector with respect to the moving reference system xy. In last chapter, last topic, kinematics of rigid body, we have discussed about the fixed reference system and this moving reference system. Now here we have to derive the equation of linear acceleration. We know the position vector RA can be written as RB plus RAB. This RA is the summation of these vector, summation of these vector and this vector from this vector triangle. Now the relative velocity VA, that is also equals to VB plus VAB. This equation also we have proved in last lectures. Then the acceleration, just differentiate this equation and you will get the acceleration. And we also know that this component is the relative acceleration of A with respect to B. It has two components, one is normal, other is tangential. This, where the tangential component means alpha into radius vector and the normal component is omega cross RAB, where omega is the angular velocity of the link AB. Hence we know these two equations. Now we will use all this formula to get the acceleration value in a problem. In the last class, last lecture, we have discussed the velocity of slider crank acceleration. Here it is the similar problem, and here we will determine the acceleration of different points and lengths. So let's see this figure of slider crank mechanism. Here this is the crank which has only circular rotation about fixed point O, fixed axis through O, and this end A, it is translating. It is the piston within this cylinder. It is only translating to and fro motion. But the link BA, it is subjected to both the motion, rotation as well as translation. Means it is subjected to General planar motion. Then to get the values, as we have to find out the acceleration, so we are starting with the given data as usually we are doing. So what is that data? The RAB 350, it is AB, it should be AB. It is the AB link, it is not G, it is AB. ROB 125, that is given, and for this link what is angular RPM, revolution per minute, that is also given 1500, and we have to find out the acceleration for a particular theta value of 60 degree. So first we find out the angular velocity, which is equals to 2 pi n. N is given, so 2 pi n, then we are getting 157 radian per second. And then this acceleration equation that already we have derived in last slide, that is AB equals to AA into ADA, where ABA has two components as we have discussed. So from this equation, let's write down the values. Alpha TV equals to alpha B into R, that is equals to 0. Why? Because it is mentioned that this link AB only rotating with constant RPM, means no angular acceleration is there, and as angular acceleration is 0, so the tangential component of this acceleration is 0, but the norm as the angular velocity is there, so normal component exists. So finally ABA, it is not AB, it is ABA. ABA equals to ANB, where ANB we know the magnitude is omega square R, omega for OB link, that we have calculated already, and the R is the radius vector length OB. So substituting this, we are getting the value of AB. Then we have to find out the angular acceleration of the connecting dot, this one, but this AB is the angular acceleration of this point B, and the two component of this angular acceleration of AB is AN omega square AB and alpha AB. You notice that for this point it has no angular acceleration, but the connected rod definitely have some angular acceleration, as it is subjected to not only this one but also a linear motion that causes the angular acceleration here. So from this equation we can write down VB equals to omega OB means the radius, and then the value is 19.625 meter per second. Then give the direction of the velocities. The link OB is rotating anti-clockwise, so VV direction is this, perpendicular to OB and towards upward direction, and as it is rotating in anti-clockwise direction, so it is rotating in clockwise direction, and hence VAB is this direction, whereas VBA is opposite. This equation is always true. VAB means acceleration of A with respect to B, it is the acceleration of B with respect to A. So both the magnitude is same and the direction is opposite. And VA towards left as it is rotating anti-clockwise. So we can draw the velocity diagram now, that already we have discussed in the last class how to draw the velocity diagram, so I am not discussing in details here. So from this velocity diagram, and as the length is given here, length of this and this is given here, so using this triangle and using sine law for this triangle, we are getting the beta value. So that beta value is required to get this value. Beta is 18. So as beta is 18 here, so this is equals to 90 minus beta. Just extend, it is beta. So this angle is equals to 90 minus beta, means 78. This is the 78. This angle is this one. This is equals to beta, this is equals to 90 degrees. So this angle actually this 72, 90 minus beta. Now from the velocity diagram, we can get the values of, as VB is calculated, so we are getting the VA and VBA value. Now the VBA value that we have determined is 10.31 meter per second, and as VBA is this VBA is equals to VBA equals to omega into R. So from here, for the link AB, we are calculating the angular velocity of BA. This calculation already have done for in the last lecture also. Now as VBA is this, and we know the normal component of acceleration AB is omega square AB into RAB, and omega is calculated here. Substitute this value. You notice that omega BA and omega AB is same thing here, same magnitude. So finally AN, so one of the component of acceleration AN AB for the link AB, angular acceleration of A with respect to B, the normal component is calculated 304.1 meter per second. Now we will try to draw an acceleration diagram similar to the velocity diagram. So what are the acceleration direction? AB, it is rotating constant angular velocity. So for this particular link, alpha is 0, and as alpha 0, for the link B, for the point B, only normal component is present, and we know normal component of acceleration is towards the center. So AB is the normal component of acceleration of point B toward the center, and then there is two component of acceleration for the link BA. As though it is only constant acceleration, constant velocity, but for this link the angular velocity is no more constant, and that's why there is an alpha, means angular acceleration is there for the link BD, and as a result there is tangential component of acceleration. It is rotating anti-clockwise, so this is rotating clockwise. Connecting link is rotating clockwise. So this direction is upward, and direction is perpendicular to this one, this link. Normal component is towards the link, along the link. Tangential component is normal to this, and this value 30 degree is given, and we calculated this should be 18. Already this is calculated. So this angle 18, it is 90 minus 18, so 72 degree. And a piston is moving left while it is anti-clockwise, so due to this connection it is moving left. So a direction is this. So number of acceleration here is 4 for this mechanism. Out of that, we know the different angles between how inclined means the direction of the components. We know the value of these acceleration, magnitude, and as well as direction. And rest of the accelerations we know the direction but not the magnitude. So let's draw a acceleration and acceleration diagram. As I have told you, NBA is the normal components along the link. This it is parallel to the link. The tangential component is perpendicular to the normal component. So tangential component is this. It is perpendicular to the normal component. This angle 90 degree perpendicular. AA horizontal direction, so this is horizontal, and the AB which is along the BO direction. This is BO direction, just parallel to this link. Here is 30 degree. This, so for this link the angle is given. Now we have drawn the entire acceleration diagram. From this diagram we are using some more simple calculations. Say here we have drawn a rectangle. Within the rectangle the acceleration diagram is there. Now individually we can calculate the these segments. This is equals to A. Now here to here, as the angle is 72 degree, so it is this ATB cos of 72. Similarly it is ATBA sine of 72. Likewise we are calculating these values. Then we can say that this plus this equals to this plus this. Similarly this plus this equals to this length. So let's write down the equations. This AB sin 60 equals to these two components, this and this. It is simply from the trigonometry. Now from this equation AB, that is unknown, calculated. Then ANB as omega BA is known, so we also know ANBA. Substitute this value and get the tangential component. Similarly, from this equation, the upper side this plus this equals to this plus this, writing and substituting this value of this and AB, we are having A equals to 994 meter per second square. And as we are calculating this absolute acceleration of point A, then we know that ATAB, tangential component of this acceleration, is alpha into RAB. Now alpha AB equals to this component as we have calculated here, divided by the radius vector RAB. So finally we are getting the angular acceleration of the connecting rod AB with the help of the acceleration diagram. The references that I have used to prepare this video lecture is given here.
So this is all about acceleration on slider crank mechanism. In the next lecture, I am going to discuss the rotation about fixed point, rotation about fixed point. And thank you for your patience, and I will expect that in the subsequent lecture you will follow similarly, and I will request you, if you have any doubt or if you think that some modification is required for the video lecture, make a comment so that I can improve this quality. Thank you.